The normal distribution. So most of us call it a bell curve. Here is the normal curvosaurus. You can even get a pillow that looks like the normal curvosaurus. So some characteristics about the normal distribution. It is what about the center? Symmetric, yeah. It is blank modal. So how many modes does it have? How many peaks does it have? 1. So it's unimodal. The mean, median, and mode are all the same. The tails are what to the axis? They get ever so close, but they don't actually touch it. It's called asymptotic. Like, I'd have never guessed that one. Remember back in your algebra class, you had horizontal, vertical asymptotes? It's kind of the idea. There's a horizontal asymptote here. Those lines, even though on the picture he has a little head, but really the lines get ever so close to the x-axis, but they never actually touch. And the last one is there's no skewness or kurtosis. So skewness and kurtosis are the measures of symmetry, or these measures of how flat or peaked is it. So skewness is a measure of symmetry about the distribution. In everything that we do, we're going to have this assumption that the data are normally distributed. The data are normally distributed. How do we know if the data are really normally distributed? Truly normal distributions have a skewness value of 0 and a kurtosis value of 0. We won't calculate it in class, but I'll show you in SPSS, or maybe you already know, where you can actually get those values. And so if it's less than 0, we say it's negatively skewed. And if we plot a histogram, we'd say that it had a long left tail. Or if that skewness is positive, it has a long tail out to the right. Now, what happens if our skewness is 0.1? That's not exactly normal. It's a little positively skewed, but is it too much? We'll typically go within the ranges of 1, positive 1 and negative 1. That will usually meet our criteria to be normal. The same thing with kurtosis. If that value of kurtosis is between negative 1 or positive 1, then we're going to go ahead and say it's normal. But a small kurtosis value indicates that the curve is platykurtic, or it's flat. Everything gets pushed down, and so the tails get stretched out. But if it's high, so 1.5 or 2, sometimes you might see 3, then it's got a big peak in the middle. And even though it's symmetric, it's no longer considered normally distributed. You might have seen an empirical rule where we use the mean and the standard deviation, and very quickly we could give ourselves some boundaries that 68% of the data are within this value and that value. If our time to complete the memory quiz really was normally distributed and the average was 40.4, and this, what was the standard deviation? 8 point what? Okay. So 8.26, then we could say that about 68%, if we're trying to generalize to the population, if this is normal, we don't know if it is, but 68% of the population would be able to complete that memory quiz in about 32 to 48 seconds. And 95% would be able to complete the quiz in subtract 2 standard deviations and add 2 standard deviations. But we could get even more specific, and we could work with standard scores or Z-scores. Remember those? Remember working with the Z table? So it is the number of standard deviations that a value is from the mean. So if the Z-score is 1, it's 1 standard deviation from the mean. If it's -2, that value is 2 standard deviations below the mean. That's kind of our interpretation. The formula is x minus x bar. Oh, that's a deviation. But we standardize it, so we divide by the standard deviation, which is why it's in standard deviation unit. Okay. On this table, we have columns of Z's, A's, and B's. So I'll just take Z equals 0.10, for instance. Can anybody find that? Tell me what is the value in column A. And what's the value in column B? 0.4602. So this information tells me that on a normal distribution, and it's standard normal, so the center really is Z, it's standardized, then where Z is 0.10, notice at the top here it says A is the area between 0 and Z. So the area between 0 and Z, 0.0398. And B column is the area beyond that Z. So this is 0.4602. If we're thinking in terms of areas under the curves. Okay? But all these values of Z are positive. What could we do with negative Z-scores? Go the other side. If our value was Z equal -0.10, tell me, what is the area between 0 and -Z? Even though I didn't draw it symmetric, it is. So we know on the flip side it's the same. And beyond Z, 0.4602. Here are some questions. Let's assume that the average time to complete the memory quiz, 45.35 seconds to complete that memory quiz, with a standard deviation of 11.927. So I want to know, what's the proportion of students, or even what is the probability that a student might complete that quiz in less than 40 seconds? So we're calculating a Z-score, I think. 40 minus 45.35 divide by 11.927. Very good. And what is that Z-score? -0.45. Yes. No, that's okay. Okay, now I always like to draw the curve on these, y'all. So if I'm thinking it's normally distributed, and in terms of Z-scores, it's centered at 0, and my Z value is -0.45. The question says, what proportion completed the quiz in less than 40 seconds, or have a Z-score less than -0.45? So that's this area right here. Now what? The table, yeah. So about 32.64% of students would have completed this in less than 40 seconds. Or the probability that we randomly choose another child and they complete it in less than 40 seconds is 0.32. Yeah? Okay, so y'all work on the next two. What is the Z-score for someone completing it in 60 seconds? 1 point what? And what is the area less than that value? Okay, let me draw it. Here's 0. 1.23 is here, and I want all of the area less than that. Okay, so that table stops at 0, right? And what does it tell you in the A column at 1.23?
Percentage above.
Mm-hmm. So the A column is between, yeah, and what is that number?
0.39.
Uh-huh. Now, is that everything less than Z? No, what is this area here? 50%. Very good. So what's the total area less than?
9.
Yeah. Okay, and then the last one says, what proportion of students completed the quiz in more than 60 seconds? Where's the more than 60 seconds on this curve? That's up here to the right. And what is that area? 0.1093 or 10.93%. Whatever happens on this side of the curve happens exactly the same on this side. So if we step over 0.1 in terms of z-scores, then the area here is going to be exactly the same as if we stepped back negative 0.1 on the left side. So the A column is the area between 0 and z, whether z is positive or negative, it doesn't matter. And B is always the area beyond Z, whether it's positive or negative. So we can't speak in terms of left-right because that would change for positive and negative, but we can talk in terms of between and beyond when it's symmetric. Okay, so now work on these two. What is the Z-score for 40? Mm-hmm. And what is the Z-score for 50? Mm-hmm. And if we draw the curve here, centered at 0, then we have Z negative 0.45, and we have a Z at positive 0.39. So now what did you do after you found those Z-scores? You used the area in which column? The A column. So what was the A column for negative 0.45? Uh-huh. And for the 0.39? Uh-huh. And the question asks, what proportion of students complete between 40 and 50? So we're really wanting all of this area. What did you get? Yeah, just add up those areas and you get 32.53%. Okay, the last one, this Z-score for 60, we already did that, 1.23. What is the Z-score for 75?
2.49.
Uh-huh. I'm going to give us another slide so I'm not down at the bottom. Okay, so here we have 2.49 as one of the Z-scores. Another one was 1.23. We know zero's here. The question says, what's the area between the 60 and 75, or between those two Z-scores? What is this area here? A few ways you could have gotten to this answer, but tell me what you did. What is the B column for 1.23? Okay, and then what else did you do? And subtract them. Right now, we don't want all of the blue column. We want the blue column minus the red column so that we're ending up with this region in between. Okay, so we just subtracted. Did anybody do it different? How did y'all do it? So you could subtract the A columns or you could subtract the B columns. Either way, you get that region in between. And what's the final answer? Yeah, and if we move that over, go ahead and put that percent sign there. So these are some important distributions. Today we have only looked at the normal distribution, the standard normal, this one right here in the middle. of the first graph. A lot of you all referenced that you might in the future use a t-test, an independent or a dependent t-test. And here we have these different t-tests. And does anybody know what that factor right there might represent? Why are there multiple t distributions? Degrees of freedom. It has to do with the sample sizes. So at different sample sizes, that t distribution looks a little bit different. Maybe it's a little flat, maybe it's a little more peaked. And the ANOVA, actually, the ANOVA test is based on the F distribution that looks like this. And notice it has 2 degrees of freedom, that D1 and the D2. So we're going to increase kind of the characteristics, get more complicated, so it's going to change the curve even a little bit more. We won't really deal much with the chi-square distribution, but it is another really common one. So I just kind of like to see all of them, how they look the same. They're actually all 4 very related to each other, and I'll mention it briefly during one of our class periods.